Hello, my name is Kolton Dean, and I will be presenting my project on graphene. So some of my colleagues in this class have already covered some 2D materials and graphene specifically, unfortunately for me, but I will try to go a little bit more in depth about the topic for my final project. So this is the 2D structure of graphene. Pure graphene is pretty much two-dimensional, but I do have a 3D model that I made that I will show off in a little bit. As you can see though, the structure of this material is completely organic, comprised entirely of hexagons of carbon, one atom thick. The hexagons are made up of conjugated pi systems, so the ring is aromatic. If you remember that concept from back in organic chemistry. There are many other 2D crystals like it, not necessarily of similar properties, but also two-dimensional, like molybdenum sulfide, and there's some stuff with antimony and phosphorus as well. While graphene is just one sheet of the structure, graphite is the same structure, but with multiple layers. Graphene is talked about because it has a multitude of desirable properties that theoretically makes it a very important discovery in the material science world. So it is often referred to as the miracle material. So here's my 3D model of graphene. So like we previously discussed, graphene is 2D and fits onto a plane, but here is my 3D model for it. I tried my best to make the bonds and atoms proportionally to scale and symmetrical, but it's a little bit iffy. Like I said, the rings are aromatic, so the bond lengths should all be about the same. Graphite structure is like this, but imagine several identical layers coming towards the screen and away from the screen, all about 340 picometers apart, held together by van der Waals forces. Okay, so let's talk about some material properties. We learned a lot about these properties in this class. So graphene is extremely strong and durable. It's harder than even diamond when they both have similar proportions. It's a tensile strength of over 1 terapascal. Remember that that's the stress a material can take before breaking. It's a Young's modulus of about 2.4 terapascals. It's impermeable, meaning it's hard or pretty much impossible for atoms to penetrate or diffuse through it, even small gases like helium. Despite it being very strong, it is still very elastic and can stretch greatly. And this isn't necessarily a mechanical property. I just threw this in here because I didn't want to have a dedicated slide, but it can absorb about 2.3% of white light and is transparent to our eyes and to light, which makes it good for touchscreens and solar cells. So its electrical and thermal properties are very great as well. It has high transmittance and low resistance. It is an excellent conductor and can carry extremely high densities of electric current, 1,000,000 times greater than that of copper. It has high intrinsic mobility and high electron mobility, meaning electrons or holes move very quickly through the material. The one drawback of graphene electrically is that it has a lack of a band gap, as it is a 2D material that has a lack of p orbitals, being hybridized, and it does not have any d orbitals. This can be circumvented theoretically by having multiple layers of graphene, which now has mass, and applying some voltage. This is now kind of a powerful tool as opposed to a drawback, as the band gap can now be tuned versus having a fixed band gap like some other semiconductors. Graphene can also be a superconductor, where charge can completely transfer through a material and there is no resistance. So, what's the catch to graphene? Well, this is actually kind of news to me, because I was under the impression that making graphene was super hard, but it's actually moderately cheap and easy to get now. However, the methods of getting it typically involve isolating a single layer from graphite. So as you might imagine, the yield for that can be pretty low. Not to mention, sometimes you may get oxidized graphene, or it may be just not be a single layer, and depending on what you want the graphene for, that can be problematic. So how do we get it? Well, one of the methods is called liquid phase exfoliation, and involves submerging graphite in a solvent with a surface tension that favors increasing the area of the crystals. With sonication, the graphite splits and individual monolayer flakes are stuck in suspension, which can be further extracted via centrifugation. Another method is graphite oxidation. Graphite is first oxidized and then ultrasonically exfoliated in an aqueous solution. The suspension is then ran through a centrifuge and then deposited as a thin film on almost any surface, and is then reduced partially in situ back to the graphene state. Large areas of graphene crystals can also be made from chemical vapor deposition on copper foils and films. So on this slide we have a plot of quality versus price and some of the applications that these have. I didn't cover some of these, like this silicon carbide one, but that's basically where you grow graphitic layers from sublimating silicon carbide wafers at very high temperatures, which also produces quite a bit of graphene. Alright, so some applications. So while it isn't necessarily good for high-performance logic circuits due to its lack of a band gap, it is good for touchscreens and organic light-emitting diodes, or OLEDs, due to some of the previously discussed properties like its resistance and transmittance. Like we discussed before, it is very strong, elastic, and thin, so it can serve very well as a coating. Graphene photodetectors are also very useful, theoretically, because semiconductor photodetectors have a limited spectral width, but graphene does not, having a far wider spectral range, ranging from infrared to ultraviolet. And because it's very inert and impermeable, it is great for drug delivery too. Here on this slide we have a timeline for applications of graphene. This is unfortunately just kind of electrically its applications, but we have some electric applications and then a timeline on when we could expect some of them. So graphene has many derivatives, but we'll just cover the most frequent one, which are graphene oxides. These were originally just seen as an intermediate or a failed attempt at producing graphene, but they now have many uses as well. As you can see, the structure is the same, just with various oxygens and functional groups attached, like alcohols or carboxylic acids. This allows the crystal to be functionalized with different functional groups added or removed or changed, which will tune the mechanical, electrical, and thermal properties to certain specifications. I like this graphic because it kind of shows the different forms here. You have your typical graphene, but then you also have your graphene oxides. Then you can reduce it further to decrease the concentration of oxygen atoms. The more it is reduced, the more it will have the properties of the original graphene, but the less functionalized it will be. So it all kind of comes back to what the user wants and what specifications they want and what applications they desire. Alright, that concludes my project on graphene. Thank you for your time.